Hello everyone, welcome to the video series on understanding FEA concepts with 1D example. My name is Vivek Varkal and previously we have already uploaded two videos on this series, and after which I have decided that I will continue explaining FEA concepts in form of video series or playlist. So in video number 1 and 2, we have seen first topic, that is understanding and deriving FEM algebraic equations using solid mechanics approach. Okay, and we took 1D bar element and we tried to understand FEM algebraic equations. Okay, so from this lecture onwards, we will see remaining topics. Okay, uh, the next one is assembly of 1D elements and what is FEM. So here we did derive uh, FEM algebraic equations for one number of element. Okay, one number of element. But here we will see how to perform assembly of many 1D elements. Okay, and that's where we will also get some clear understanding of what exactly FEM is. Okay, then we will see framework of FEM theory and deriving FEM algebraic equations using FEM method. Okay, till now we have done for 1D bar element using solid mechanics approach. Okay, so here we will see with FEM method. So we will derive the same algebraic equations but with FEM method. Okay, and these particular topics I am thinking like they might take no, no, couple of hours. So this might be like a couple of videos on these two topics. Okay, then we will try to understand the difference between analytical and FEM solution. So that's where we'll get why exactly FEM is needed. So we'll have some that understanding. Okay, so till now we would have done no understanding the concepts with 1D example. That is nothing but 1D element. Okay. Then next we will see some different types of elements. Okay, and we will also see stiffness metric for some of these element types. Okay, so we'll not derive the stiffness metric as we would have done for 1D element, but we'll just overview for stiffness metrics for some of these element types. Okay, okay, so let's start. Okay, so we will see assembly of 1D elements. So let's summarize previous two videos. Okay, so what we have seen, like we have derived FE algebraic equation for 1D bar elements, 1D bar element, yeah, which is nothing but force vector. Okay, force vector is equal to stiffness matrix, okay, and displacement vector for 1D bar element. Node 1, node 2. So okay, and we have also seen stiffness matrix properties. We have said that we cannot solve this problem. We cannot solve this, okay, if there is a rigid body transformation. That means we must give some constraints or boundary condition. Okay, rigid body transformation. Okay, so let's with this let's start today's topic, uh, assembly of 1D elements. Okay, so till now what we have seen, uh, we took a structural member. Okay, we have taken some structure. Okay, and we have represented it into equivalent element. Okay, bar element. Okay, so what we actually did, okay, so complete assembly or structure was represented as one number of element. Okay, one number of element. That means we have discretized this structure into one number of element. Okay, so what if we divide or discretize this structure, okay, into finite number of elements? Okay, so we can do that. Okay, for example, I will divide this into, and I can represent it something like this. Okay, I can do this. So this is nothing but discretization. Discretization. Okay. So when we applied discretization on assembly, we got finite number of elements. So this is the main idea behind finite element method. Okay. So what is that? FEM. Okay. We can also say that it is a discretization of domain into finite number of elements. Finite elements. With this, what we get? Okay. Okay. So if you recall, okay, what we have seen when we discretize. Okay, when we discretize, we have got only one element. Okay, so we get only two nodes, right? And we have seen the unknowns in FEA equations were u1 and u2, right? That means we are solving the problem at two number of points. Okay, corner nodes. Okay, what if we want to get the solution at intermediate points like this? Okay, that means we have to divide it into number of finite elements. Okay, so one element, discretizing with one element is not enough, so that's why we discretize it to with so many number of elements. Okay, that means we get the solution at intermediate points also. So with this analogy, we can also know, we can understand FEA something like this. Okay, if I have a structure, okay, which will have infinite number of points, infinite points. Okay, when I apply FEM to this structure, okay, I get finite number of points. That means finite elements. Okay, so this is the main idea behind finite element method. So let's try to understand assembly of 1D elements. Now what we did, like we have discretized it with let's say some here three number of elements. Okay, so next what we have to do, assembly of these 1D elements. Okay, here there are one, two, three elements, so we have to perform assembly. So let's try to understand with example. Okay, okay. Let's take two. Okay, let's divide it with only two number of finite elements. Okay, just for ease. Okay, so I have a structure which I have divided it to two number of finite elements. Okay, the this finite element one, this is the element number two. Okay, so stiffness for element one is k1, stiffness for element two is k2, right? And this is a node 1, node 2, and node 3. Okay. So what I'll have, u1, okay, force vector f1 for here displacement at node 2, u2, external force f2, displacement at node 3, u3, and force at node 3 is f3. Okay. So what actually no we do with assembly. Okay. So these are the steps. Okay. First we discretize, okay, into finite number of elements, into finite number of elements. Next what? So right now I'm just giving no steps. Okay, we'll see with this particular two elements example. Okay, then write FEA equations or element characteristic equations for each element. Okay, for each element. Okay, so for example here two elements, so we have to write FEA algebraic equations for each of these two elements. Okay, next what? Then we perform assembly, that we will see. Okay, after performing assembly, what we get? We get global system of equations, global system of equations. Okay. And the main part of this global system of equations is that that also looks very much very much like FEA equations of single element. Okay, so this also looks something like k into u is equal to f. Okay, but the size will be different. Okay, this size will be different. Okay, for example, if we divide it into n number of finite elements, okay, let's take n number of finite elements, then size will be n by 1 displacement vector, force vector size is n by 1. Okay, and n by n is the stiffness matrix. So I'm talking about 1D elements. Okay, so these are the steps. Okay, let's apply this onto this particular example. Okay, so first we have discretized into two number of finite elements. Okay, now we will write down FEA equation for each element. Okay, so this is also like here also we can say something no, a solid mechanics kind of approach. Okay, if I have particular structure, okay, consisting of two members. Okay, if I draw free body diagram, it will be something like this, right? So here also we are not doing nothing but we are drawing free body diagram for element 1, for element 2 with stiffness k1, stiffness k2. Okay, node 1, node 2 for element 2, node 2, and node 3. Okay, we can write something like this. Okay, this is solid mechanics principle, like each member we have represented as a free body diagram. Okay, now we will write FEA equations for both of these. Now we know the FEA equations from previous two lectures we have seen. It is f1 f2 k, this stiffness matrix k minus kk, and u1 u2 vector. Okay, so we'll try to apply this on this. Okay, so for element 1, for element number 1, okay, we can say f1 f2. Okay, now this superscript is node, for node. Okay, I will, for element I'll put subscript. So f1 1, f2 1, okay, is equal to, okay, uh, this should be subscript. Okay, this should be subscript k1 and k2. Okay, So because k is nothing but element stiffness, subscript I will use it for element indication. So k1 minus k1 minus k1 k1, okay, and displacement vector u1 u2 for element number 1. Okay, so we have just applied this FE algebraic equation which we derived, okay, for single element. We used it for this particular element, okay, element number 1. Similarly, for element 2 also I can write, okay, f1, sorry, f2 force at node 2 and force at node 3. This belongs to element 2, so f2 to f3 2 is equal to stiffness of stiffness matrix for element 2, k2 minus k2 minus k2 and k2, okay, and into displacement vector. So u2, u at the node 2, displacement at node 3. This belongs to element 2, so 2 2 subscript. Okay, so this is step 1 we have finished, and step 2 also we have finished. We said discretize into finite number of elements, then write FEA equations. Okay, write FEA equations for each element. So both of this we have finished. Okay, now what we'll do, we'll do assembly. We'll do assembly. Okay, so here if you see, assembly is nothing but just a mathematical operation here. Okay, I have here, from here I have two equations. Okay, and here also I have two equations. Left hand side I will have, in this equation left hand side I have force vector, force at node 1 and force at node 2. Similarly for this equation one, I will have two equations. One uh, one equation will have on the left side force at node 2 and force at node 3, right? So when I combine these two equations, 2 plus 2 equations, when I combine I get three equations. Okay, because unknowns are three, so two equations I will get three equations. It is just mathematical operation we are doing. Okay. So if I put it some, okay, if I combine them, so I will get something like this: f1 from element 1, f2 element 1 plus f2 element 2. Okay, this one, this f2 from element 1 and f2 from element 2. Similarly, I will have f3 from element 2 is equal to k1 minus k1 minus k1 plus k1, okay, and plus k2 minus k2 minus k2 and k2. This will be 0. Okay, and here u1 1, u2 1 plus u2 2 and u3 2. Okay, so I'll just further simplify this. Okay, f1 at 1, okay, f2. Now I'll remove this subscript. Okay, because I have only force, I will have now single force vector, and external force at each node there is a single value. So I will say f1 f2 and f3 is equal to k1 minus k1 k1 plus k2 minus k1 k2 minus k2 minus k2 k2, and this also I'll write u1, u2, u3, because displacement at node 1, node 2 and node 3. Okay, so this is what we get. Hope. Okay, so this is what we get final equations. Okay, and if you see, when we said when we apply assembly procedure, okay, we get a global system of equations. So this is our global system of equations. Okay, this is called force vector. This is this one is called displacement vector, and this one is called global stiffness matrix. Okay. So from element stiffness matrix we have got global stiffness matrix. Okay, so if you see, this vector size is 3 by 3, sorry, 3 by 1, 3 by 3 and 3 by 1, right? So as we said, for element equations we have seen, right? For 1D element it was 2 by 1, 2 by 2 and 2 by 1, right? K, F vector and displacement vector, sorry. Okay, force vector and stiffness, element stiffness matrix and displacement vector. Okay, so node 1, node 2. Okay, so this element is 2 degree of freedom element, 2 DOF element. Okay, 1 degree of freedom for each node, and that's how we got 2 by 1, 2 by 2 and 2 by 1. Similarly, when we perform global when we perform assembly of connected elements, we get global equations, right? Global equations. Okay, and if those if we have, for example, we discretize into, let's take n number of elements. Okay, n number of elements. Okay, our global equations will be, force vector will be n by 1, okay, is equal to global stiffness matrix, which will be of size n by n, okay, to displacement vector, which is also n by 1 size. Okay, so this is key takeaway. N number of elements means n degree of freedom. Now this complete system is n degree of freedom system, right? Okay, okay. Uh, okay, sorry. So there is small correction here. Okay, if I discretize it into n minus 1 number of elements, then I will have n number of nodes, right? So for each node, 1 degree of freedom. So system will be n degree of freedom for n minus 1 discretization. Okay, and that means n degree of freedom is nothing but n number of nodes. Okay, so n by 1, n by n, n by 1. Okay, so we have derived the FEA equations, FEA algebraic equations for complete assembly. Okay, and what next? Once we get this one, okay, once we get this, what next? So we have just got the equations. That's it. We just apply loads and boundary conditions, and we solve the problem. Okay, so if I rewrite these steps now again. Okay, we discretize into finite number of elements. we wrote down FEA equations for each element. We performed assembly. Okay, and that's how we got the global system of equations. Okay, and next is apply loads and boundary conditions, okay, into global system of equations and solve the problem. That's it. Okay. So I hope this is clear. Okay, assembly of 1D elements and how FEM works. What is the core concept behind FEM? That is nothing but discretizing the structure into finite number of elements. Okay, so I have just one homework. If you, want to do this homework, this is good practice for you. Okay, this will make your understanding more clear. If you have any doubts, okay, by doing this practice or exercise, your doubts also will get clarified. Okay, so I'll just give you a problem definition. You can do this as an exercise. Okay. Okay, so this is a structure. Okay, and this structure is constant at one end. Okay, uh, the structure stiffness matrix K1 K2 is given. Okay, and length is also given. Length L1 L2 is given. Okay. And we apply, let's take no, external force of 10 kilonewton on this and at another end. So one end is fixed, another end is applied some external force. Okay, so I'll give you the values also. Okay, so let's take area. Okay, you need K1. K1 is nothing but A1 E1 divided by L1 and matrix 1 minus 1 minus 1 1. Okay, so I'll give you the values and you can get K1. So A1 is okay, I'll give you R1, okay, radius, so you can get A1. So this is circular. Let's say this is a circular cross section. Okay, so R1 is 25 mm. Let's say R2 is 50 mm. Okay, then L1 is, let's take a zero point 0.5 meter. L2 is 0.25 meter. So you have to convert the units. Okay, you have to, so there is always a unit consistency you have to maintain. Generally what I have seen in industries, most commonly used unit system is Newton, mm, sorry, second and tons. Okay. This is the most commonly used unit system in the industries. uh, there could be a different unit system, but this is widely used in most of the industries. Okay, so if I follow this unit system, okay, my stress will be in units of Newton per mm square, which is nothing but megapascal. Okay, so I'm giving you value, you have to maintain the unit consistency. Okay, this is also kilonewton, this also you may have to convert. So the problem I'll just mention. So there I'll give you two exercise. Okay, number one is uh, divide divide each cross section member. Okay. For example, this one, first member you divide it into one number of element. So one element for, okay, L1 L1 length member. Okay, and discretize second L2 member, L2 length member. Okay, again with one element. Okay, so it will be something like this. So for this problem, okay, all loads and boundary conditions are given. Okay, you can solve the problem means we have to find, okay, uh, u1, all the unknowns. Okay, I will not tell. You have to find all the unknown displacements. Okay. And second problem is, uh, each uh, each length, okay, L1 and L2, we will divide it into two number of elements, two elements. Okay, two elements for L1 member, and discretizing L2 member as well with two number of elements. So it will look something like this. Okay, element, this L1 member, and this is this representation may not be correct. Okay, L1 is zero point 0.5, L2 is 0.25. Okay, so this may not be correct, but you hope you understand. Okay, zero point 0.5 meter, and L2 is 0.25 meter. Okay, so this will look something like this. I'll put big dot here just to differentiate. So two number of elements for L1 and L2. So for this also, what are the displacements, unknown displacements you have to find. Okay, so this is the exercise, and in next lecture, next video, I will also give the solution for this. Okay, but before that, if you know, if you have not seen that video, please solve on your own this exercise. You have to do it on your own. Okay, you will have to brainstorm little bit, but it will be a very fruitful. Okay, it is worth practicing it on your own. Okay, so with this, this is the end of the lecture. Okay, in the next video, I will just summarize this, the summarize from this particular lecture and continue. Okay? Thank you, everyone.